Welcome, everyone, to today's Protocol Labs research seminar. Our speaker today is Mohammad Jalalzai. Mohammad is a postdoctoral researcher at the Blockchain UBC Cluster. He received his master's degree from TU Berlin and his PhD from Louisiana State. And nowadays he does research on distributed systems, specifically efficient and scalable BFT consensus algorithms for blockchain networks. And today he will be telling us about one such algorithm, Fast-HotStuff, which builds upon HotStuff and addresses some of its limitations with respect to latency and robustness. I will be posting a link to the paper in the chat. And Mohammad, the floor is yours.
Thank you, George, for introduction. Today I will be talking about Fast-HotStuff. This is a joint work with Jianying Niu, Chengfen, and Fang Yu from UBC. So first we will talk about the HotStuff protocol and what led us to think of designing a new consensus protocol to address some issues that we encountered with the HotStuff protocol. So, and then we will discuss how the Fast-HotStuff protocol addresses those issues or limitations. This talk will mainly be about the pipeline or chain HotStuff. There's a specific reason that why we are talking about pipeline or chain HotStuff. I will tell you guys in a minute. So we know that HotStuff is a state-of-the-art consensus protocol, and basically it solved the complexity issue during the weave chain, because most of the consensus protocols previously had complexity issues in terms of message complexity or authenticator or signature complexity during the weave change. And HotStuff was the first protocol that successfully addressed this problem, and hence made the weave change very efficient because in most cases, weave change was a cause of bottleneck in many consensus protocols previously. The chain HotStuff, since HotStuff improved the weave change performance by linearizing the message complexity as well as authenticator complexity during the weave change, this helped the protocol to employ rotating primary mechanism. And this rotating primary mechanism basically adds additional characteristic in the protocol, and that is very important and desired properties for a protocol used in blockchain setup. So rotating primary first allows the protocol to provide a fair opportunity for each primary to propose a block. So in case if there is some rewards associated with proposing a block, then each primary gets a fair shot and fair chance to propose their respective block. The second is that the rotating primary mechanism, whenever primaries are selected randomly, helps us to make it difficult for malicious attackers to perform denial of service attacks on the primaries, because when primaries are chosen randomly, it gives the attacker a very small time window to pinpoint or find out who's the primary and then attack it. So these two properties are desired properties that we have in the chain or pipeline HotStuff consensus protocol. And that's why we were more interested in change and pipeline or pipeline HotStuff protocol. So we see how the message exchange pattern basically works in the HotStuff. Generally, a primary, or in this case here, we have P1, P2, P3, P4. These are the primaries that are chosen through during time T. And so a primary receives votes from previous for the previous block from replicas, and then builds a quorum certificate of it from these votes. Quorum certificate is basically a collection of more than 2/3 of votes, just to prove that more than 2/3 nodes have voted for that specific block in case of a blockchain. So we consider a block or a proposal, and adds this QC into its own block, and then proposes its proposal to the network. And then the network verifies it, sends their vote to the next primary. The next primary builds a QC. It's the same way, collects the votes when builds a quorum certificate, adds the quorum certificate to the block, proposes to the network, and the same pattern gets repeated again and again. So basically, we see that here the primary aggregates the votes, builds a block or a proposal, and the next proposal contains QC as well as the new block or the new set of transactions. This way, the QC itself basically as also acting as the pointer to the previous block or to the parent block. The QC is basically points to the parent block. So so if we look into the memory of a single replica in the network and how this chain is stored there based on the voting rules, we can see that if we have a block B1, then it has a QC from its parent, and then we may have another block B2, block 2 added, another proposal added to the chain, and the QC in this protocol is basically quorum certificate for the block 1, and hence it points to the block 1 as its parent. Similarly, the next block is added. And once we have 3 blocks built over the top of a block, so in this case on block 1, if you have 3 blocks built over the top of it, and first 2 blocks have a consecutive weave numbers along with the first block, then the first block can get committed. So this consecutive weave number condition for the first 3 blocks is also called 2 direct chain, because we make like 2 direct chains here. This requirement is called 2 direct chain. So if this chain is broken, then you cannot have a commit. Then the chain has to wait so that this condition is satisfied somewhere later on, so that the commit takes place. So this is how a chain a chain looks like inside a single replica using a HotStuff protocol. One of the points in the HotStuff voting rule is that in HotStuff, as the blocks are added, the protocol allows primary to use an old QC or an old pointer to point to an old block, and hence generating a fork. But a primary or a malicious primary can only generate the fork, it can use an old QC that can point to the grandparent of the most recent block in the chain. It cannot point to a block older than the grandparent. So it can only point to the grandparent or parent while doing the forking. So it cannot point to any block older than the grandparent of the most recent block. This forking, it's because there's a lock. There's a lock at the grandparent based on the protocol. So any pointer that is older than the any QC that is older than the grandparent of the most recent block, it will be rejected. So but it can still cause a fork and revoke and the 2 blocks, at most 2 blocks from the chain. And based on the rules of the protocol, since in this case block 5 is the most recent block, the next primary will extend the most recent block. So it will extend block 5. So in this case, this forking basically revoke 2 of the blocks from the chain. This has different adverse implication or the protocol performance. First, the resources that spent on proposing these 2 blocks and proposing and verifying these 2 blocks are wasted, basically. Secondly, the throughput is affected. So the throughput of the protocol is reduced due to the forking attack, because now the commit does not occur, because if you remember, we talked about the two direct chain, because the direct chain or consecutive numbers of the weave number of this chain of consecutive weave number is broken. So now block 2 will only be committed if somewhere along the chain later on this two direct chain rule meets. So we have additional latency. We have these, and the transactions in block 3 and 4 have to be reproposed because they are revoked. And at the same time, if these blocks are from honest primaries, then the blocks of the honest primaries are moved from the chain. This means the transactions that honest primaries propose are removed. So this also affects the chain quality and may even help the Byzantine primaries to censor or significantly delays some specific transaction if they want. We did some initial tests on a network of size 40 and analyzed the effect of the forking attack on average as well as in worst case. On average, the primaries are randomly selected, and if it's a Byzantine primary, it's simply revoke or does perform the forking attack and revoke any honest, up to 2 honest blocks before it in the chain. And we see that when the number of Byzantine nodes in the network reaches the maximum, then it significantly reduces the throughput of the network. And then we also analyze the worst case scenario. In the worst case scenario, the nodes are chosen in round robin manner. And when nodes are chosen round robin manner, the worst case can be that malicious primary selected after each 2 honest primary. So we have 2 honest primaries selected, and then there is a malicious primary, and again 2 honest primaries selected, and then again there is a malicious primary. So this gives opportunity for malicious primaries to revoke the blocks proposed by the honest primaries. So this significantly reduces, as we see in the black curve on the graph, significantly reduce the performance. And majority of the chain now will comprise of the blocks proposed by the malicious primaries. And if malicious primaries choose to propose smaller blocks, then this curve can even go down. We choose to have the same block size for honest as well as malicious primaries. And then if we zoom in a little bit more to see how the chain looks like in the worst case, this case can also happen in the average case, but it looks, but we will consider the worst case because it's easy to show the worst case than the average case. So this upper chain, the rectangles here show the primaries. So we assume that we have primary number 1, 2, 3, 4, 5, 6, 7. So we have 7 nodes, and each of them is selected as a primary in a round robin manner. And primary 4 and 7 are Byzantine or malicious. And then the chain at the bottom, this shows basically the state of the chain and the memory of a replica in the network. And so if we see that the primary 1 propose a block during the VV, and it's added into chain. And then when primary 2 and 3 propose a block, they are revoked by the forking attack from primary 4. So now we only have a single block from primary, we have a block during the VV plus 3 from primary 4. And the same thing repeats again. Primary 7 revokes the blocks from primary 5 and 6 who are honest. And then we have a block from the malicious primary v plus during the v plus 6, and so on. But if we analyze this chain, we can see that during n number of weaves, while n is the size of the network, during n number of weaves, we will only have the chain will be committed only once. So after n weaves, the chain will get committed only once. So this is a significant delay. So here we see that somehow this two-direct chain gets completed. So we have like a consecutive 3 blocks over the top of each other, and then we have the 4th block. So block number 7 gets committed. A block proposed by the primary number 7 gets committed, which is v plus 6, and then the whole chain gets committed. And this also occurs here. So if we have this block proposed by the primary number 7 before primary 1, then we have a two-direct chain here. So since we can see that here we have 2n or 2n times blocks are proposed, but blocks are committed only 2 times. And at the same time, if we see that the chain is occupied mostly by the blocks proposed by the Byzantine primaries, whereas after each n proposal, only 1 block is from an honest primary, whereas all the other blocks and n proposals are from Byzantine primaries. During the average case, it's a bit better, like it's kind of approximately 50-50. So like approximately or more or less half of the blocks are from malicious nodes and half of the blocks are from honest primaries. But in the worst case, it's there is only 1 block after every n weaves. There will be only 1 block added into the chain from honest primary. So this significantly reduces the quality of chain. So to address these problems, these mentioned problems, we designed a new consensus protocol called Fast-HotStuff. Its message pattern is similar to the hot stuff. So it's as we discussed, the primary builds a QC or quorum certificate from votes received for the previous proposal. It adds this QC into the block and proposes into the network. The network sends the vote to the next primary. The next primary builds a QC again, and so on. So this message chain pattern is similar to the hot stuff. So we try to, during normal phase, so we try to keep the message complexity linear during the normal phase. And now if we take a close look at the memory of a single replica and the network, how it looks and how the voting rules in the commit rule in the protocol, how the commit rule in the protocol works. So basically when 2 blocks are added over the top of a block, then the first block gets committed. So basically we have reduced the latency by 1 round trip. And then next condition is that the 2 blocks should have the consecutive weave number. So block 1 and block 2, and in this case, for block 1 to get committed, block 2 has to be from consecutive weave number. But block 3 might be from any other weave number, doesn't matter. Here we see that we reduce the round trip by 1 message, we reduce the latency by 1 message round trip. How we were able to achieve it? Basically, we added condition in the protocol that whenever a primary proposes a block, it has to provide proof that the QC it is including in the block is basically the recent QC. The recent QC held by majority of honest nodes, or a recent QC has higher weave number than the QC held by the majority of the honest nodes. So it's either the latest QC, it's a latest QC held by a majority of honest nodes, or it's even newer QC, or with the QC with a higher weave number than the QC being held by a majority of honest nodes. So this proof basically prevents the forking attack, because now the malicious primary cannot use an old QC to form a fork. And if it tries to make use an old QC, that proposal can simply be rejected in the network. So this proof can be provided in two forms based on which state the protocol is operating. So in happy path, when there is no failure in the network, this proof can be provided in such a way that the QC of the weave of the block that is being proposed is one more than the QC it's holding. So in other words, if we consider, for example, block number 1, the weave of the, if we assume that the weave of the block number 1 is, let's say 100, then the weave of the QC that it's holding has to be 99. This shows that the QC is not old, and it's the most recent QC. Now, if there is a failure in the network, so this was relatively straightforward. Now, when there is a weave change in the network, and then the next primary, after the next primary that comes after the weave change, and this primary has to propose a block. Now, this primary has to provide 2f plus 1 QCs, have to include 2f plus 1 QCs in this proposal. And this inclusion of these 2f plus 1 QCs are included in a structure. We call it aggregated QC. Just for simplicity, we call it aggregated QC. And then you can show the proof that, okay, out of these 2f plus 1, f plus 1 can be honest from honest nodes, and at least one can be a QC that is held by the majority of honest nodes. That will be the latest QC. So that's great. We solved this problem. Okay, we provide this proof. But now we go back to the square one. So HotStuff was developed to address the to improve the weave change. This means to by linearizing the weave change part of the consensus protocol, basically make the weave change more efficient and avoid the bottleneck during the weave change. And now when we are including 2f plus 1 QCs, we get quadratic message complexity, and also you get like quadratic signatures included in the QC, because each QC is built, might have aggregated signature, but it's built off of n-f words. So we back again to the square one. We now our weave change is somehow similar to the weave change of the classic BFT protocol like BFT. So how to address this? So first we try to reduce the number of QCs being exchanged during the weave change, but we find it out that it is not, we couldn't, it cannot be done, at least by us. So we spend a lot of time, but we couldn't find any way to do it without, do it efficiently, so that without compromising the safety lines of the protocol. Then we try to dig a bit deeper and see what are the actual factors that we get the performance reduction during the weave change when we exchange like quadratic messages or quadratic authenticators or signatures. So we decouple the transmission cost and the verification cost of the QCs. So in order to understand what's the main problem, and see if we can address that main issue. So we find out that the transmission costs, especially in cases of blockchain, when the block size is generally large, for example, for a block size of 1 MB in network of 100 nodes, this aggregated QC, or this quadratic size of the aggregated QC, is just 1.5% of block size. So basically, it does not affect the performance a lot. So this transmission of this aggregated QC or does not affect the performance of the protocol a lot. So it's not the main issue, at least for the network sizes that generally PBFT operates. But the main issue lies with verifying this aggregated QC that is built from the N-F or 2F+1 QC. The verification cost is like we did a small analysis to see that how expensive it can be in comparison to the signing a QC. So verification cost of a single QC is 546 times higher than the signing a QC, and it's around 800 times higher, or it takes the latency that this causes. The latency, it's not the actual the computing cost, but the latency it causes, like 800 times more than the aggregated signature, and 546 times more than a signing QC. So the verification of this a single of aggregated QC is very expensive. So if we see that the verification of single QC is so much higher than the other than the signing and aggregating for aggregated signatures, then the aggregated QC, when you have 2F+1 QCs, then this cost gets really high. Then we focus on reducing this verification cost. Okay, if we cannot reduce the transmission cost, can we reduce the verification cost? Because this is the main issue of the bottleneck during the weave change. Instead, instead of focusing on the decreasing the message size, the message complexity, we focus on decreasing the computational complexity, because this was the major issue we found. So we found that luckily we were able to exploit the quorum size, the quorums basically, to avoid verification of the aggregated QCs during the weave change, but only one aggregated QC has to be verified. So basically when after the weave change, when the new primary is selected, it aggregates the QC from all other nodes, or from 2F+1 nodes, and then propose a block with the aggregated QC, and then each node has to verify the aggregated signature of the aggregated QC and the aggregated signature of QC with the highest weave, or the latest QC, and this aggregated QC. And only these two, verification of only these two QC is enough. And so therefore, instead of verifying 2F+1 aggregated signatures, a node has to verify just 2 aggregated signatures. And this significantly helped to improve the weave chain performance. And why only 2 is enough? So because when a replica or a node receives aggregated QC, when it verifies the aggregated signature of the aggregated QC, it implies that the QCs and this aggregated QC are from 2F+1 distinct nodes. So we already know that it has been sent by 2F+1 distinct nodes, and out of this 2F+1, F+1 are honest. And when F+1 are honest, then there will be at least one QC, and out of this F+1 that will be held by the majority of the honest nodes, and which will be the highest QC held by the majority of honest nodes, or maybe it can be even most recent QC than the highest QC held by the majority of honest nodes. So this meets the condition, the condition that we put, that the primary has to provide the proof. And so we can verify this proof just by verifying two aggregated signatures instead of two F+1 aggregated signatures. But yeah, as I said, we could not reduce the message complexity, but the message complexity does not affect the performance a lot, because the message size during exchange, during weave change, is too small. So even those quadratic, if they get quadratic, it's still with less than 2% of the block size. And then we did some tests, some performance tests on AWS network. As you can see, the blue curve shows the performance of the latency of the Fast-HotStuff when the block size is 1 MB and there is no failure in the network. And this green curve shows the latency of the Fast-HotStuff when aggregated QC is used. We assume that the previous primary failed, and then after the GST, we have a synchronous period. So we did not consider the timeout period. So we just assumed that the network has recovered and the next primary proposed a block with the aggregated QC. So we see that there is a small increase in the latency because the inclusion of the aggregated QC. But in both cases, Fast-HotStuff has better latency than the HotStuff, and the latency of the HotStuff increases faster when there is a forking attack, and because the forking attack basically breaks that two-direct chain rule, and the chain has to wait for the completion of that two-direct chain so that the blocks can be committed. And in terms of the throughput, when the block size is 1 MB, we see that during the normal case, Fast-HotStuff has slightly better throughput than the HotStuff. And the HotStuff's performance shown by the black line, the throughput in the black curve, reduces significantly during the forking attack. And the same pattern can be seen when the block size is 2 MB. So then we try to dig a bit deeper why the HotStuff has Fast-HotStuff has a slightly increased throughput than the HotStuff, because basically, if you see, the pattern is same, so their throughput should be somewhat similar. But why the Fast-HotStuff has relatively better throughput? And then we find out that since Fast-HotStuff uses threshold signatures to achieve linear weave change and to reduce the cost of signature verification, but the problem with the threshold signatures is that the cost of calculating the threshold signature from the partial or the shares that the primary when the primary receives those shares is really high, and this cost basically causes quadratic time complexity due to the calculation of interpolation at the primary. So, and we can see that when the primary receives the shares or the partial signatures, it builds the threshold signature. So it takes really long time, and the primary. And the x-axis, we have the network size or the number of signatures received by the primary. So we see that it increases really fast. It's the red bars. So basically, when the primary, although like theoretically we see that that the threshold signatures helps to achieve a linear weave change, but in practice, if we see the primary there is a delay in the primary because of the building threshold signature. And this delay in the primary, when the causes the delay throughout the protocol, throughout the network, because all the nodes in the network or replicas in the network are blocked. They are waiting for a proposal from primary, while primary is busy calculating the threshold or building the threshold signature. So this was the main reason why there is a slight reduction or dip in the throughput of the hot stuff. Whereas on the other side, the verification cost of the aggregated signatures and the verification of aggregated signature and the nodes increases linearly. It's shown in the blue line. And we use aggregated signature. So that's why there's a slightly additional latency in the primary, which blocks the network for some time and causes the reduction in the throughput of the hot stuff. We also did the test of the wide area network. The results, the pattern is the same, but it's the latency difference is huge because it's latent. It's wide area network. So, but it's really huge, and when there is a forking attack. So if you see that the latency when the block size is 1 MB gets really, really high when there's a forking attack. But the overall pattern is not very different. Yeah, so that's our results that we achieve over the WAN environment. And as a conclusion, I would like to say that Fast-HotStuff lies somewhere in a sweet spot between the hot stuff and the classic BFT protocols that have a high complexity during the weave chain. So we try to combine the best of both worlds in a single protocol. And of course, we have to make some compromise too, but the main goal was to achieve higher performance and get the best of both of the world in the middle. So for example, Fast-HotStuff has efficient weave chain like a hot stuff. It has rotating primaries as a hot stuff. But unlike hot stuff, it's really robust against the forking attack. And also it has lower latency than the hot stuff. Whereas if you compare it with the protocol like PBFT, so Fast-HotStuff has a faster weave change compared to the PBFT. Fast-HotStuff has a linear message complexity during a normal protocol operation, and Fast-HotStuff has a rotating primary, where rotating primary mechanism can be employed or PBFT, but then since weave change is very expensive, it affects the protocol performance a lot. So overall, our goal was to somehow combine the best of both of them and propose a new protocol. And yeah, that was our goal, and we tried to achieve in Fast-HotStuff. Yeah, that's all from my side. Thank you.
One question. I was wondering whether you are familiar with the Aardvark work, this work by Lorenzo Alvisi, Mike Dallin on making BFT protocols more robust, trying to fix those problems with sequencers that are slow, nodes that flood the network, and so on, and whether you believe that these ideas could be integrated within your protocol or not easily.
I don't remember the exact, it has been a long time, like maybe it's like 3 or 4 years ago I read that paper. But I guess there is always room for improvement. So the main goal of Aardvark, as I hope I remember correctly, was that to prevent the Byzantine primary from delaying the proposal for a long time.
Yes, exactly. Yes.
So I guess Fast-HotStuff has somewhat natural defense against this attack, because you prevent, so since the primaries are rotating, so if a byzantine primary delays proposer for some time, it cannot delay, then it will be replaced. So it will not be like,
it cannot delay forever. Yes, it cannot delay forever.
Yes, but it will still affect, on average, it will still affect the performance, because the same bad primary might be selected again, because you have a limited range of nodes, and they will be selected. So on average, it will affect the performance. So so the solutions, I guess, and the hardware protocol can be employed here to add additional defenses against such attacks.
That was my guess too. Okay. Thank you very much. Thank you.
Thank you for that.
Do I understand correctly that the happy path is still the same as the normal HotStuff and doesn't have to carry those aggregated QCs?
The normal path is similar to the HotStuff, so it does not carry aggregated QCs, but it has an additional, it has additional information. Well, even it doesn't have additional information, but the verification of this fast path by each node is that they have to make sure the QC is the latest QC that is included. So like message pattern wise, it's same, but each replica or node has to verify that the QC that a block is carrying is the latest one. So this condition, this is different than the HotStuff, but the actual message pattern is same. Yeah, so there will be only one QC.
So basically no additional cost in the happy path.
Yes, there is no.
You just view number. You check the view number is consecutive or not.
Yes.
So you mentioned that the message transmission time and the extra transmission time of this aggregated QC is negligible, and the verification time is non-negligible. But if we compare the verification time with the latency in the network, especially wide area network, geo-distributed system, would you think that even the verification time would also be negligible in terms of end-to-end latency of individual transactions?
It won't be negligible, but it will like diminish. You are right. So it will be. It will not be as significant as it is in the LAN environment, but it will still be significant. And also, end-to-end latency is something that at the consensus level, probably, there are ways to maybe reduce it, but usually, if nodes are located, if primary is located far away, so then there probably you don't have any other way to reduce the end-to-end latency unless you change the infrastructure. But this verification cost, although it won't be as significant as it was in the LAN environment, but it is not negligible either. And it's our best shot to reduce it. And it's the only part that we can basically improve and the weave change.
If there is a way to improve it, why not? Yeah, because it doesn't seem to introduce any additional complexity. So it's not even a compromise, right? The compromise is introducing those aggregated signatures in the first place, right?
Yeah. So basically, aggregated signatures that aggregated QC are transferred or sent, but you only verify 2 of them. So you don't verify 2F plus 1 plus 1. So yeah, you just verify 2 of them, although they are sent. But the smaller overhead that we anchor is very, very, the size of that is small. So, but it is a compromise. Like, it will be great if we couldn't, if we could find out some way to do it without it. But we couldn't do it. And I'm not sure if it's possible. That means, But as HotStuff did, they did it, like they only sent QC every time, even after the view change. But then it has, but then they have compromised the latency, and then the protocol is vulnerable to forking. So yeah. So we thought maybe this might be a better compromise.
Yeah. So it seems that the original HotStuff was still over optimized for the best case, and not for the worst case under many attacks and really Byzantine behavior.
Yeah. Thank you, everyone. Thank you, George.
Thank you again to Mohammad for his great talk. Thank you also to all the attendees, as well as those of you watching the recording. If you'd like to be informed of future talks, funding opportunities, and more from Protocol Labs, you can go on our website at research.protocol.ai, scroll down to the very bottom and sign up for our mailing list, where you can customize the types of emails that you want to get. So thank you so much, and see you then.